Dear students, welcome to EPG Pathshala. I am Dr. Y.S. Rajput, former Head of Division, Animal Biochemistry Division, National Dairy Research Institute, Karnal. Today, I am going to teach you about the basic concepts in electrophoresis technique under the paper Biochemical Techniques. Electrophoresis refers to movement of charged particles in an electric field, leading to their separation. Particles must be charged. Only charged particles will be migrating in electric field. If charged particles migrate at a different velocity, it will result in their separation. Small molecules such as amino acids, nucleic acids, peptides, and macromolecules such as proteins, nucleic acids can be separated in an electric field. Whether potential difference, potential gradient, distance between electrodes, viscosity of the medium, size of the particle, and pore size of the support can change the migration rate or not. These are some of the aspects covered here. Whether charge on particles can be changed. What are the requirements of performing a successful electrophoresis techniques? These aspects are also covered in today's presentation. Fundamentals in any technique should be very clear because this can help in solving many of the bench problems. In this presentation, our focus will be on to understand the concepts relevant to electrophoresis technique, which deals in movement of charged particles in an electric field. Thus, in this presentation, we will also explain what determines the charge on simple molecules such as amino acids and finally a macromolecule like proteins. As buffers are used during the electrophoresis of the protein, it is essential to understand buffers, how these buffers can be selected for the electrophoresis. These aspects are also covered in presentation. Another objective of the presentation is to make you familiar with the requirement in performing electrophoresis techniques. Let me first define electrophoresis as movement of charged particles in an electric field. There are two essential components in it. First, the particle must be charged and electric field is required for their movement. It is also essential to understand that electrophoresis is a separation technique and separation is based on differences in velocity of charged particles. Also, separation occurs before these particles approach respective electrodes. When voltage is applied across the electrodes, electrodes become charged. Electrodes carry either positive or negative charge. So voltage V is applied between the two electrodes. During electrophoresis, voltage is applied across the electrodes and this generates potential gradient, which is a function of not only applied voltage denoted by V but also by distance between two electrodes denoted by a small d. Potential gradient is calculated by dividing voltage V with distance between two electrodes small d. It is made clear here that different electrophoresis equipments may differ in distance between electrodes, and therefore even at the same applied voltage, potential gradient will differ. Students are always advised to see what is the distance between the two electrodes and don't use blindly the voltage applied for generating the desired potential gradient. Force exerted on charged particle in an electric field depends not only on potential gradient denoted by capital E, but also on quantity of charge denoted by small q on charged particle. This force is equal to multiplication of potential gradient, that is E, with charge, that is Q. So the force is equal to E into Q. This force causes charged particles to move in electric field. Cations carry positive charge and move towards cathode. Similarly, anions carry negative charge and move towards anode. If charged particles reach electrodes, these will be neutralized there. In electrophoresis, voltage is stopped before charged particles reach electrodes. For students, it is essential to note it that in electrophoresis, always you have to stop the voltage before the charged particles reaches there. Otherwise, these will be neutralized at the electrodes and separation will not be achieved. Here in this slide, we will be dealing with electrophoretic velocity or mobility. Velocity of charged particle, that is capital V, not only depends on force exerted on it in an electric field, but also on friction created by medium in movement of particles. This friction is constant under given experimental conditions and referred as frictional coefficient. Velocity is inversely related with frictional coefficient. More the value of frictional coefficient, lower will be velocity. Frictional coefficient will be dependent on viscosity of buffer, pore size of the support, and size of macromolecules such as protein. Temperature affects viscosity and therefore it will affect frictional coefficient and ultimately velocity. Electrophoretic mobility term may carry similar meaning to velocity. This point is not clear to many of the students, and at times they feel mobility and velocity, they are similar and identical terms, but in actual it is different. It is the ratio of velocity v to potential gradient. Electrophoretic mobility is the ratio of velocity to potential gradient. It is to be noted that velocity is dependent on distance between the electrodes while electrophoretic mobility is not. In this slide, our focus will be to make you understand that how much heat can be generated during the electrophoresis. Besides that, we will also link this process to understand that what are the various factors on which the heat generated can be controlled. In electrophoresis, I am repeating it again that electric current is switched off before these ions reach the respective electrodes to allow their separation. Heat generated is given by equation, that is W is equal to I square R, where W is the power generated in watts, I is the current, which increases with increase in voltage as per the Ohm's law. So that is, if voltage is increased, then current will increase at a constant resistance, and R is the resistance. So it is clear that the moment we increase the current, the heat generated will be increased by the square function of the current. So one should be careful that not to increase the current during the electrophoresis. Otherwise, all the artifacts related to the heat generation electrophoresis will be observed in electrophoretic techniques. As I said earlier, that heat is generated during electrophoresis, and heat can damage significantly the objective for which the electrophoresis is performed. It can result in subsample and buffer ions to diffuse more when the temperature is increased, and so this will result in broadening of bands, that is the separated molecules in electrophoresis. It can also result in decreasing the viscosity, and thus resistance of the medium will also decrease, and as per the Ohm's law, it will result in increase in current at a given voltage. So by increasing the temperature, the current will increase, and further increase in temperature will result in more increase in current and more generation of the heat. So this becomes a continuous process if we do not control the applied voltage. Then more heat will be generated, and this generated heat will result in broadening of the bands. Also, it will denature the proteins and enzymes, which will lose the enzyme activity or protein activity on separation. On many of the occasions, we are interested to know or measure the enzyme activity or protein activity after separation of molecules. If heat is not taken care, then it will result in inactivation of these activities, and we will never be able to observe the activity of these separated molecules after electrophoresis. If during electrophoresis constant voltage is used, current will continue to slowly increase with time because of heat generated. More is the value of current, more is the heat generated. Thus, this increased amount of heat will further increase current. As such, amount of heat will be continuously increasing with time. Some workers prefer to run electrophoresis at constant current. That it should be clear that higher is the current, higher is the heat generated, and higher is the velocity. In order to minimize the heat generation, low voltage should be an option. However, this will end in long separation time, which ultimately will also result in diffusion of separated bands. Effects of heat can be minimized if support is maintained on low temperature. This is achievable if electrophoresis is performed at low temperature, or cold water is circulated through buffers in electrode chambers, or support material is layered over the surface with good heat conducting properties, or through Peltier cooling. It is also repeated here that force exerted on charged particles is dependent on voltage, not on current. It is therefore advised to perform electrophoresis on constant voltage, which when applied should not result in generation of excess heat and also should not lead to diffusion of separated bands. Here in this slide, we will be telling that what determines the charge or net charge on macromolecules such as protein. This requires the understanding of pH, pK, buffer, isoelectric point, dissociation of water, dissociation of weak acid, Henderson-Hasselbalch equation, concept of buffer, and chemical nature of protein. As you already know that amino acids are building blocks of proteins, that is, protein molecules have several hundred amino acids. So it is essential to understand what these amino acids are. In order to understand the concept of pH, it is essential to understand the dissociation of water. Water is a solvent for many biochemical reactions, and therefore most of the reactions in biology, they are carried out in water. So it is essential to know to what extent a water molecule can be dissociated. This is shown by equation where H2O is in equilibrium with hydrogen ion and hydroxyl ion, and the equilibrium constant K is denoted by H ion concentration multiplied by hydroxide ion concentration and divided by undissociated water molecule or water concentration. And this is equal to 1.8 into 10 to the power minus 16. Based upon this, since the concentration of water is constant, and if it is multiplied by the equilibrium constant, a new constant is written as ionic product of water, or that is denoted by Kw, which is equal to equilibrium constant multiplied by concentration of water. I may tell you that concentration of water even after dissociation remains constant, and once we say concentration of water, I am talking about the undissociated water molecule. Very small fraction of the water exists in the dissociated form, and the ionic product of water, that is equal to H ion into OH ion, is equal to 1.8 into 10 to the power minus 16 multiplied by water concentration in undissociated form, or equal to the total water concentration. And the value of the water concentration is 55.6. So if we multiply it by 1.8 into 10 to the power minus 16, the ionic product of water will come out to 1 into 10 to the power minus 14. So this is the extent of dissociation of water. So it is clear that very small amount of the water exists in the dissociated form. As I explained earlier, that hydrogen ion concentration from dissociation of water is very, very low. It could be in the range of 10 to the power minus 0 to 10 to the power minus 14. And depending upon the hydroxide concentration, the concentration of H ion or hydrogen ion can be calculated. This is the reason that a simplified version of representing the hydrogen ion concentration is defined in terms of the pH, where pH is defined as the negative logarithmic of hydrogen ion activity, which is equal to hydrogen ion concentration for dilute solution. So there is slight difference between the hydrogen ion concentration and hydrogen ion activity. Only for the dilute solution, the hydrogen ion concentration is equal to hydrogen ion activity. Hydrogen ion activity is hydrogen ion concentration multiplied by activity coefficient, which approaches to unity at low ionic strength. So that is essential, that pH measurement is essentially to done to represent what is the hydrogen ion concentration, and also a very simplified version so that everyone can understand easily. Once we write the pH values, one can easily make out what could be the hydrogen ion concentration. Similarly, on the lines of the pH, we can define the pKa. This is also a negative logarithm of the dissociation constant, and this is used when we are talking about the dissociation of the weak acids, where the dissociation is also very, very low, similar to the dissociation of water. So similar to the explanation given for defining the pH, the pK value is also defined so that one can have a very simplified version of knowing what is the value of the dissociation constant. As I said earlier, that hydrogen ion concentration, hydrogen ion activity, these are related with each other, and a term has come as the activity coefficient, and also it is known that the activity coefficient reaches unity when ionic strength of the solution is very low. So let us know what is this ionic strength. Ionic strength is defined by using a equation which says that this is equal to half of summation of Cz square, where C is the concentration of an ion and Z is the charge on it. So that means if a solution of sodium chloride is there, we have to take into account the concentration of sodium ion and charge on sodium ion. We have to take into account concentration of chloride ion and the charge on it. This is true when the salt is completely dissociated. So that means if you calculate this ionic strength of 1 molar sodium chloride, it will turn out to be 1. But if we see the case of the calcium chloride, which on dissociation gives calcium ion and twice the concentration of the chloride ion, calcium ion carries the 2 positive charge and chloride ion 1 negative charge. So if we use this particular equation, then from 1 molar of calcium chloride, the ionic strength will be 3. So in terms of the molarity of the two solutions, sodium chloride and the calcium chloride, molarity is 1, but in terms of the ionic strength, calcium chloride will have 3 times more ionic strength as compared to sodium chloride. So this way one should understand how the ionic strength can be calculated by using this particular equation. I will be explaining the basic equation used for the dissociation of weak acid, which is popularly referred as the Henderson-Hasselbalch equation. Here in this equation, Ha is any weak acid which is dissociated into H ion and the dissociated form of the acid, where dissociation constant Ka is equal to H ion into A minus divided by Ha. Ha refers to the undissociated state of the acid, or H ion is equal to Ka into Ha divided by A minus. If we take the logarithm on both the sides, then this turns out to be log H plus is equal to log Ka plus log of Ha over A minus. Since we have already defined the pH and pK, pH is minus log of hydrogen ion concentration and pK is minus log of Ka. So let us convert the sign of this equation. This turns out to be minus log H plus is equal to minus log Ka minus log Ha over A minus. So if we put this value, this pH for the minus log H ion and pK for the minus log K ion, then this equation turns out to be pH is equal to pKa plus log of A minus over Ha. I may repeat it here that A minus refers to the dissociated state of the weak acid and Ha refers to the undissociated form of the weak acid. So if we have, then for the weak acid, we must know what is the Ka value or the pK value, and if we know the pH, we can find out what is the extent of dissociation of the weak acid at a given pH and the pK value. In continuation of Henderson-Hasselbalch equation, where we have explained the importance of pH and pK for determining the dissociation of weak acid. In this table, we have given the values of the pK for phosphoric acid, citric acid, boric acid, carbonic acid. These acids have more than one pK value, depending upon how many protons are present in these acids. Phosphoric acid has 3 pK values, citric acid also has 3 pK values, boric acid again 3 pK values, and carbonic acid 2 pK values. On the other hand, acid like acetic acid, base like tricine or tris, these have only 1 pK value. So it is essential that when we want to know the extent of dissociation, then one should be careful that which pK value is to be used while using the Henderson-Hasselbalch equation. Equation is referred as Henderson-Hasselbalch equation. This equation establishes the relationship between pH, pK, and the dissociated and undissociated states of weak acid. This equation can give information to what extent any group is dissociated and to what extent any group is undissociated. The dissociated states and the undissociated state of a particular group can bear a charge, may not bear a charge. If we see the dissociation of amino group, its undissociated state carry a 1 positive charge, whereas its dissociated form carry no charge. In contradiction to it, the carboxylic group in undissociated form do not carry any charge, whereas dissociated form carry 1 negative charge. This is regarding the situation of an amino acid where an amino acid contains 1 carboxylic group and 1 amino group, and these can contribute to the charge on the amino acid. However, when amino acids are linked to another amino acid through a peptide bond, which is the true situation case of the protein molecule, the 1 amino acid which is used in peptide bond formation and carboxylic group of another amino acid which is also in peptide formation, these will not contribute to the charge on the molecule. However, if we see a protein molecule as a large molecule which contains large number of amino acids, still it has N-terminal amino group and C-terminal carboxylic group. These groups will contribute to the charge on the protein molecule. In protein molecule, we have a number of amino acids whose side chain will also contribute to the charge. Groups contains any dissociated form of it. Like in case of the aspartic acid, glutamic acid, we have the carboxyl groups. Like in case of lysine, we have amino group, and these groups can exist in the dissociated form and undissociated form, and dissociated form, undissociated form of these molecules will contribute to the net charge on the protein molecule. So this is important to understand that what could be the pK value of each group, and that pK value at a given pH will dictate that to what extent any group is dissociating or to what extent any group is existing in the undissociated form. So through this route, one can find out what could be the total charge on the protein molecule, and once the total charge on the protein molecule is known, then in electrophoresis one can find out what could be the quantum of the force which a molecule that will be exerted on protein molecule in electric field. In this slide, we will be explaining what are buffers and how these buffers are selected. Buffers are defined as solutions which resist in change in pH on addition of acid or alkali. If we see the chemistry of these solutions, these are the mixtures of weak acids and its salt or weak base and its salts. Buffers are selected on the basis of required pH and pH range of the buffer, and we must understand that all buffers are not suitable for the entire pH range, and this is how we will know from the pK value, which I explained earlier, that this will be used for selecting a buffer. For a typical buffer, for stabilizing the pH, then pK value should be, for selecting a buffer, it is essential to know what is the pK value of its weak acid or weak base. Only the buffer can stabilize if the pH range is within 1 pK unit. This is how the buffers are selected. For example, if acetate buffer is to be selected, its pK value is 4.76, then it can only give a buffering effect if in the pH range of 3.76 to 5.76. So for ideal situation, one should always select a buffer whose pK value is in the range of the required pH for any biochemical reaction. In this slide, we have shown the structure of an amino acid, which contains the amino group and carboxylic group, and one hydrogen atom and one group referred as R group. And in this structure, there are two groups, NH2 and COOH, whose dissociation can contribute to charge on amino acids. R group can also have some dissociated groups for certain amino acids, and whose dissociation can also contribute to the charge on amino acid. In this slide, we have shown you that how two amino acids can combine through peptide bond, and this is essential that this kind of joining of amino acids leads to the protein molecule. If we see this joining where alpha carboxylic group of first amino acid and alpha amino group of second amino acids, they are used in peptide bond formation and will not contribute to charge. In protein, we have large number of peptide bonds. Besides that, we have N-terminal amino group and C-terminal carboxylic group, and these two groups will contribute to the charge on protein molecule. Amino groups and carboxylic groups, which are used in peptide bond formation, will not contribute to the charge on protein molecule. As I said earlier, that amino acids have R group, and some of the R groups may contain ionizable groups, which can contribute to the charge on protein molecule. These R groups are not used in peptide bond formation, and that's the reason that these can contribute to the charge on protein molecule. For example, side chains of aspartic acid, glutamic acid have carboxylic group, while that of lysine has amino group. Similarly, imidazole group of histidine can contribute to the charge. Thus, pK of alpha amino group, epsilon amino group, alpha carboxylic group, beta carboxylic group, gamma carboxylic group, imidazole, and hydroxyl group from serine and threonine. It is essential to understand what is their pK value. It is also essential to understand what is the number of these groups in a protein molecule and what is the pH in which the protein is solubilized, because all these three things will contribute in defining the net charge on the protein molecule. When we talk about the dissociation of the groups, many of us are confused and believes it that a group on dissociation will contribute to the charge. But that is not always true. If we see the dissociation of carboxylic group, then on dissociation it acquires one negative charge. So in case of carboxylic group, undissociated form is uncharged, while dissociated form carry the one negative charge. While in case of the amino group, on dissociation, it loses one positive charge. So it should be remembered that when we are talking about the dissociation amino group in protein, like in case of the alpha amino group or N-terminal amino group or amino group from the lysine, then on dissociation it will reduce one positive charge, and pK values of these groups which are present in the R in amino acids are given in the next table. You will know that the pK values differs from one group to another group, which is given in the next table. As we have said earlier that pK values of the groups in protein are different for the different groups. For alpha amino group, which is present in all amino acids, pK values varies from 8.8 to 10.6. Epsilon amino group 10.53. Carboxylic groups like alpha carboxylic group, beta carboxylic group, gamma carboxylic groups, pK value is less than 4.25 but variable. Guanidino group of arginine, pK value is very high, that is 12.48. Imidazole group of the histidine, pK value is 6. Sulfhydryl group 8.18, and phenolic group in tyrosine is 10.07. So this value is variable. So that means at a given pH, the extent of dissociation of these groups will be different. Some of the groups might be completely dissociated, some of the groups might be undissociated, and some of the groups might have dissociated form and undissociated form at a given pH. As I said earlier, that pH and pK determines the extent of dissociation, and which can be calculated from the Henderson-Hasselbalch equation. But a simplified version is that when pH is equal to pK, there will be 50% dissociation. When pH is 1 unit higher than pK, there will be about 90% dissociation. When pH is 2 units higher than the pK, there will be about 99% dissociation. When pH is 1 unit lower than the pK, there will be about 10% dissociation. And when pH is 2 units lower than the pK, there will be only 1% dissociation. So this is a very simplified version of the Henderson-Hasselbalch equation, and this will tell to what extent any group is dissociated at a given pH when we know the pK value of these groups. Here in this slide, I will be explaining what we understand by isoelectric point. Isoelectric point of protein is the pH at which net charge on molecule is 0, and at this pH, protein molecules will not migrate in electric field. Electrophoresis of protein is carried out in a buffer. If pH of buffer is higher than isoelectric point, protein will acquire negative charge and will move towards the anode. Similarly, if pH is lower than the isoelectric point, protein will have positive charge and will move towards cathode. Extent of net charge, either positive or negative, on a particular protein will be increasing as pH of the buffer moves away from the isoelectric point. This is now summarized how one can calculate the charge on protein. It requires certain good calculations for knowing what is the charge on the protein. We have to find out the number of individual amino acids in protein whose side chain carry charge. Also, one has to find out what is the pK value of such side chains. Then calculate the extent of dissociation of each side chain at the pH of buffer and using its pK values and also the Henderson-Hasselbalch equation. This will help in calculating the charge contribution from each side chain. Also take into account charge contribution from N-terminal amino acids. It is also significant to note that same protein will carry different net charge at different pH values. Also, it is true that proteins with different pI values will have the different net charge at the same pH. So this is how the charge difference for the different proteins at different pH, this overall concept is used for the separation of the molecules in electrophoresis. When we perform any technique, there are certain requirements. Here are some of the most essential requirements for conducting electrophoresis are given. It includes power supply, electrophoretic unit. Naturally, it is different for the different kind of electrophoresis, which we will be covering in some other modules. It requires dispensers. It requires cold room facilities, especially for overcoming the heat effects in electrophoresis. Then photographic facilities, which requires after the completion of the electrophoretic run, and some of the gel documentation systems for viewing the electrophoresis after run, and certain small things like plastic supplies, including the tips and the other essential requirements which are present in the laboratory. We have covered basic concepts used in electrophoresis. It is clear that charged particles, small particles as well as large particles can be separated in electrophoresis. It is also to be noted that only charged particles can be separated. Charge on the particles can be changed by changing pH. By changing pH, mobility of particles can be changed. Besides change in pH, frictional force is also equally important, which can control the mobility of charged particles in electric field. So many of the separations are now using the migration of charged particles in electric field by manipulating the frictional forces. These concepts will finally help in understanding the specialized electrophoretic techniques, including acrylamide gel electrophoresis, agar gel electrophoresis, capillary gel electrophoresis, and isoelectric focusing. Thank you.